Welcome back, and in this video we're going to be looking more at the electron structure. In the previous video we introduced the idea of the SPD notation in A-level chemistry. We're now going to go on and look at using that in practice and how it relates to the electron structure of the atoms and the elements. So you're going to need your notes, and we're going to start on page 4. So we have to learn or remember this order of filling, going from the 1s to the 2s, 2p, 3s, 3p, 4s, 3d, and so on. We have to remember that electrons will fill the lowest energy orbital available. They will go in one at a time before they pair up. That you cannot fit any more than 2 electrons in any one orbital, and the only reason you can fit 2 in there is if they have opposite spins. If there are several orbitals of the same energy level available, electrons will go in singularly before they will pair up. So let's have a look at some examples. So we're going to start with potassium, which has 19 electrons. I'm going to put those into our boxes. So remember, the numbers represent the principal quantum shells and the letters represent the subshells. So I've got 2 electrons in my first orbital. That's now full, so I'm going to move to the 2s. Then I'm going to move to the 2p. You'll notice I'm putting them in singularly before I pair them up. Then I'm going to go into 3s. Then I'm going to go into 3p. And I've got one more electron, and that's going to go in my 4s. Sodium has 11 electrons, so I'm going to put 2 again in that first subshell, 2 in the second, and then filling up my 2p. Again, I've got 1 electron left over, and that's going to go in the 3s. So you can see that the electron configuration of potassium and of sodium is very similar. It's just potassium has an extra shell of electrons. Nitrogen is one that catches students out a lot. It's got 7 electrons in it, so I'm going to fill up these 2. Then I'm going to put the next 2 electrons into my 2s. And this is why you need to practice putting them in singularly first of all, because when we put them in, we will see that nitrogen fills up with 3 single electrons in each of the orbitals. And that helps to explain things like why nitrogen generally forms 3 bonds. So if I did 3 covalent bonds, I could share 1, 2, 3 electrons. Oxygen, on the other hand, has 10 electrons. Oxygen, on the other hand, has 8 electrons, so I've got 2 here, and then again I'm going to fill up singularly, but I this time got an extra electron, so it does have to pair up. And this again explains why oxygen generally forms 2 bonds, because I can share a pair of electrons in those last 2 orbitals. Fluorine, with its 9 electrons, again, filling it up, you have a space here to make 1 bond. Phosphorus has 15 electrons. So I'm going to draw the electron configuration of phosphorus. Again, notice it looks very similar to nitrogen's, as you would expect, because they're in the same group in the periodic table. Last but not least, we're going to do magnesium. So again, I've got my electrons, and I've got my 2 electrons in my third principal quantum shell. Again, if you look back, it's very similar to calcium, except calcium has 1 more shell. So when we come to write out the electron configuration, we need to give details about where the electrons are. So the first thing you come to is the number. That represents the principal quantum shell. The letter gives you the subshell, and then the superscript gives me the number of electrons in that subshell. So 1s2. So for example here, sodium has the electron configuration 1s2, 2s2, 2p6, 3s1. It's telling me that I've got one electron in my third principal quantum shell in subshell S. We're going to have a go at doing that for the ones we've done on the previous page. So for potassium, for example, we have 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. So you can see the similarities between sodium and potassium. Nitrogen, if you remember, 1s2, 2s2, 2p3. So it's telling me I've got 3 electrons in the p subshell. So there we've written them out for you. Notice the order of the filling, 1s2, 2s2 and so on. So we can use these not only for the main block elements but also for the transition metal elements or the D block elements. So for example, iron would have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, because if you remember the S of the principal quantum shell 4 is lower in energy than the D, and then we'd be back to fill up the D and it'd be 3d6. These two, the 4s and the 3d, are very close in energy levels. The next example would be vanadium, and again we would fill up the inner shell electrons in the same way. 4s2, and this time it would be 3d3. Now there are 2 exceptions to this rule, and that is chromium and copper. Now because chromium, because if you remember that 4s and those 3d orbitals are very close in energy level, well, I can borrow one of the electrons from the 4s and put it into the 3d to half complete. So if you look at the 3d orbitals, if you remember there are 5 of them. So 3d5 would have 1 electron in each orbital of the D block, and that's slightly what we call screens the nucleus, and it makes it slightly more stable. Copper is another example where this comes into effect. So again, I've got my inner shell electrons all filled up, but I've got 4s1, so I can have a 3d10. So those are the 2 exceptions that you need to know. There's one more thing you need to know about these electron configurations of transition metal elements, and that is the fact that although the electrons go into the 4s first and then into the 3d, they're so close in energy that putting the electrons in causes these 2 orbitals or these 2 subshells to change places. So they go into the 4s first, but they also come out of the 4s first. So for example, if I was to make an iron 2+ iron, I would lose those 4s electrons first. So Fe2+ has again all these electrons, and quite often we just use argon to stand for the inner shell electrons, and then these electrons would be lost and I would have 3d6, 4s, 0. So there'd be no electrons into the 4s and 6 electrons in my 3d. So first in, first out. So it could become quite long when we try to write out all the inner shell electrons, and as it's really usually only the outer shell electrons that I'm interested in, I quite often use the nearest noble gas to stand for the completed inner shell of electrons, and then I just add the outer shell electrons. So that's just a shorthand version of writing those electron configurations. So we can not only use this for atoms, we can also use it for ions as well. So if we look at the sodium cation, we know how many electrons it will have. There are now no electrons in the 4s because it's been lost. So I get 1s2, 2s2, 2p6. Again, with the fluoride ion, I've got that extra electron in my 2p orbitals. So this becomes again 1s2, 2s2, 2p6. And you should see that these two now have exactly the same electron structure. We say that they are isoelectronic. In other words, they've got the same electron structure as each other. They've actually got the same electron structure as the nearest noble gas, which would be neon. So there we just completed the rest of those electron configurations on the bottom of page 6. Notice where we've got quite long electron configurations, we quite often shorten them to that abbreviated version. So for example, bromine there becomes argon, and then we add on the extra electrons. The oxide anion is O2-, so it's gained 2 electrons. So they've gone in there, and the calcium is Ca2+, and it's lost the electrons from its 4s subshell. So on page 7 of your notes, we can see that an orbital is just a 3D region of space where there's a high probability of finding an electron. And the different orbitals actually have a different 3D arrangement. So 1s, or the s orbitals, are spherical. So that's a 1s and a 2s. So they both got the same shape. They're both spherical. So the p orbitals, well, we know there are 3 p orbitals, px, py and pz, and they're orientated along the Cartesian axes, and they're shaped like dumbbells. Now these 3 all have the same energy level, so it doesn't matter which one of these you fill first. So the d orbitals are slightly more complex, and there are 5 d orbitals. F are even more complex, and there are 7 of those. You don't need to be able to do the shape of these ones. You do need to be able to do the shape of the s and the p orbitals, but you do need to know that there are 5 d orbitals, and we'll be studying the d block in more detail in the second year. So if you look at page 8 of your notes, we can see these electron density plots. So you can see here, this is your s orbital, and it's a roughly spherical shape. These are your p orbitals, and they correspond to your p orbitals, to those dumbbell shapes. The last p orbital would look identical to these two, but orientated along a different axes. So you've got px, py and pz that correspond to the Cartesian axes. So looking at our 2s orbitals, 2s and 3s, we should be able to see that 3s is slightly larger than 2s, and 2s, if you like, sits inside the 3s orbital. So you can think of them a little bit like Russian dolls. So we need to remember that each subshell has a particular number of orbitals. So the s subshell has 1 orbital, the p has 3, the d has 5, and the f has 7. So that means, in terms of the total number of electrons that each can hold, well, each orbital can hold 2 electrons. So we're just going to times all these numbers by 2. So I have 2, 6, 10, and 14. So what I'd like you to have a go at doing is filling out the table on page 9. So I've written out there for you the electron order of filling, starting with the 1s and finishing with 4f. Couple of things to remember. The 4s is filled before the 3d. This also applies to the 5s and the 4d and so on. So you've got to remember that bit. But you also have to remember first in, first out. So electrons will be lost from this 4s before they are lost from the 3d. Once both of those electrons have gone out of that 4s, then you will start taking electrons from the 3d, but not before that 4s is empty. You need to be careful, however, of chromium and copper, where you've borrowed one of those electrons to partially or totally fill that D subshell. So have a go at that. So that just finishes this little video looking at the electron structure. And hopefully you'll begin to see that it makes a little bit more sense than the model you learnt at GCSE. And you should be able to realise how it relates to the periodic table. So we have here my periodic table, and you should see the familiar layout with 2 elements and then a big gap between the next 6. And the reason for this is that these are my S block elements. So if you think about the electron configuration of lithium, it's 1s2, 2s1, and then beryllium would be 1s2, 2s2. But when I move across to boron, here I'm moving into my P subshell. And that is why you'll see this block here sometimes labelled as your P block elements. We keep going until we get to calcium, and then we move into scandium. And that's why this block here is quite often called the D block elements, sometimes also known as the transition metal elements. And the reason for that is we are now into the D elements. So calcium would be argon 4s2, but scandium would be argon plus 4s2 3d1. So hopefully it starts to make a little bit more sense when you consider the periodic table. So in the next video we're going to look at the evidence for shells and subshells and orbitals. But that's in the next video. So until then, take care, stay safe, bye bye.